Hello everyone and thank you for joining. I'm Omri. I'm from Microsoft's Azure Defender for IoT group. Today I'll be talking about two remote code execution vulnerabilities I found in a popular physical security system, which you probably also know as an alarm system. I won't only be talking about those two vulnerabilities, but I'll also be showing you a full exploit chain leading from the vulnerability itself up until the point where the alarm is disarmed. So we don't have a lot of time. Let's start. Some general background information. I wasn't actually working on this specific project. I was working on another project. I was looking for vulnerabilities in an open source network stack called LWIP. It's a pretty popular one, mainly with the low-end devices. So while looking around at Shodan, I found a lot of devices that I use LWIP and are connected to the internet, and I wanted to figure out what are those devices. So surprisingly, the majority of those devices were from the same LWIP version, which was super interesting to me. So I looked around it and tried to figure out what are those devices. So looking at some device, for example, from Spain, some endpoint, you can see that it has an interesting banner that says you must activate your JavaScript and some login page in here. So, and another endpoint, for example, from Romania, has this a very similar banner and a login page that looks almost the same. So after digging for a while with this information, I finally understood that it was a product from a company named Paradox. Paradox is a popular Canadian manufacturer of physical security systems. And more specifically, what you saw earlier in Shodan came from this network model, IP150 internet model, which works with the whole range of alarm systems that Paradox manufacture. So fast forward, we got the equipment, and this is it. So what you see in here, in this little metal box, is actually first the control panel, the SP4000. Control panel in the alarm system jargon is the main board, is the motherboard, is where everything connects to. Then we have the internet module in here with some cheap plastic on it. So after peeling the plastic, you can see that it's quite a simple board. In here, we have an ARM chip on it, which came from ST Electronics. It's an STM32F chip, which is an ARM compatible chip for embedded devices. Then we have this keypad in here, which you probably know it's in most places it's installed right next to the door, and you can put the code and arm the alarm system before leaving the building. And besides that, we have the power supply in here. So I cropped the image a bit so we can talk about protocols. So first we have the internet model. It goes to the public internet via standard Ethernet connection. And on the other side, it connects to the control board with a proprietary serial protocol. So the IP150 is actually a kind of a bridge between Ethernet and serial protocol. On the down part, we have the keypad, which also connects with the same serial protocol. And we didn't purchase those, but generally speaking, the sensors and the sirens would connect also to the control board. That's how it looks like on my desk. There is the laptop in here. It connects directly, and we'll later see how and why. So let's start with the fun. In those kind of projects, the first thing that I want to do is normally getting firmware updates because I want the firmware itself, and that's the easiest way to go. So I got this device. It's called this software. Sorry, it's called Infield. Paradox supplies it to the clients in order to install firmware updates on the whole range of devices. So this is actually an older version of Infield than the current one. I chose that because it gives me the option to select what I want to download and download it locally. So I chose the internet model and got the file, which is named IP150, the version, and .path. I suspect that the path is a Paradox update file, maybe Paradox update format. Anyways, I asked Minwalk to check it for me and didn't get any result. And looking at the entropy, it's pretty clear one. It seemed to be encrypted or might be compressed, but I guess that encrypted. So let's just take a quick look on the firmware itself. It's a comparison between version 4 and version 3 of the firmware for the same device. We can see that most of the data in here is actually the same between both versions. We can see that we have the version ID, probably the version ID in here, and that we have the data itself, the encrypted or compressed data in here, which is different. So at that point, I wanted to either decrypt or decompress the data. I assumed it might be XORed or some simple encryption, simple standard encryption, because of this repeated pattern, which most of the time indicate it's a simple XOR encryption, but wasn't very successful with that. I fought with that for a week, and doing the fast forward thing again, I finally looked online, and I was able to find in some GitHub a post from a guy which goes by the name of Nesmogos, which did excellent work decrypting the firmware, and he actually uploaded it for everyone who wants to play with reverse engineering in 2018. So I actually reached him because it's an old post. I reached him and I asked, and he suggested that he'll decrypt the newer version for me, and finally, I got the decrypted a firmware, which strings looks like that. So we have the header, we have some server in here, and we have a lot of some kind of data. So what is that data? It's actually Intel hex encoded, and Intel hex works like that. So we have the separator in here, and each a part describes some kind of data and where it should go, checksum, and the byte count, the size. So I just quickly took a Python library, fixed some bugs in there until it worked, and finally I got the decrypted payload, which the firmware actually loads only in memory, and did some strings on it, and we can see immediately that there is something interesting in here. Although it's not quite the firmware, there's a lot of strings in here, and the header seems to indicate that it might be some kind of internet bootloader. So now, starting with the reverse engineering, I loaded everything to GDRA and immediately spotted that there is something in here, those addresses that seem to make sense, taking into account that most ARM firmwares start with a vector table, which describes the initial stack pointer, the main function, which goes by the name of reset, and some other interrupt handlers. So that seems pretty good, taking into account that the memory ranges in here, that's an image taken from the datasheet of the STM chip. The memory ranges of the RAM matched the stack pointer address, and the flash, the firmware itself, matched those addresses. So that must be our main function, which is a really good indication. So I just went over and reverse engineered the firmware. I needed to guess the base address so things would come along nicely. It seemed like there is no operating system, no real-time operating system, just a plain firmware. And it seems that it does only fetching a firmware from a remote server. using some proprietary protocol and which is also encrypted. So taking a deep breath, we'll start. I set it up man in the middle, where the device, the alarm system, connects to my laptop, which dumps the network traffic with Wireshark when it goes to the server. And on the other hand, I used infield in the VM to tell him to start. That's a newer version. And just tell the device, go and start update. Then I was able to dump the whole communication with Wireshark. And I got that. So on a brief look, I was able to spot the encrypted firmware because it started with EB619C, which I knew from exploring the path file that is the beginning of the encrypted data. And for a fairly good reason. EB619C is always this header IP 150 on the decrypted path. So that's pretty good news. It seemed to be encrypted with the same encryption algorithm used in the path file. And there is some header in here. So the header itself is made up of a magic number that is just compared, a packet size, which is little endian encoded, and a checksum, which is a really simple cumulative checksum. They just count all of the bytes together and get a 2-byte checksum. And regarding the encryption, I did a quick Python script, which is just a Python version of the encryption algorithm from the firmware decryption algorithm. So it looks pretty similar. The encryption itself is not, I think it's proprietary encryption. It's not very complex, but not very simple either. So I just did the script and tried to decrypt the data. And those are the strings that I got. So you can see that we have some kind of an HTML file in here, and that we have several other HTML files by name, some memory manager exceptions, some registers in here. Seems pretty good. It seems like the actual firmware to me. So just to summarize up until this point, we got the device. We decrypted the path with the help of our friend, decrypted the X encoded in-memory payload, reverse engineered it, and using the man in the middle setup, dumped the firmware from network and decrypted it. And now we're getting to this point, to the point where we can actually investigate how the web interface works, this login page. And we know there is some involvement of LWIP in here, and there is some web server, but that now we're in the state where we really want to explore that part. So LWIP, as I said, is a pretty popular open source. Each vendor has to implement only the network interface, and then we have like the IP layer, the TCP, and high-level protocols such as DNS, and applications like web servers. Specifically, the web server that comes along with LWIP is a pretty nice web server, and it's a static one also. So the way that works is that as a programmer, if I want to use index.html, for example, I'll go and use a make fs data utility that comes along with LWIP. And that utility will actually take the data from index.html and encode it as a variable in a C file. So afterwards, on the actual device, I could use fsopen, which is an implementation of a virtual file system that will go back to that C file and fetch the data and supply it to the application, to the web server, so it could send it back as a GET response. And everything is pretty tight. The implementation is simple. The http.c holds all of the web server itself. And then we have the make fs data utility. And that's just an example files that you can use. So that's like the fsdata.c that comes along with the project. There is some index HTML encoded in here, and you can see that it also includes like the HTTP headers and the server header, content length, and the data itself. So let's talk about the vulnerability itself. At this point, we have like, as the user, we have the connection page, which behind the scenes uses JavaScript, some legacy function called login encrypt, which actually encrypts the user code with RC4, then it hashes it with MD5 and X encoded, so it could be safely passed as a username and password. I think the username and password split is for legacy purposes. So it just encrypts, hashes, and X encodes, and everything is passed as get parameters to the server. Now, on the server side, what Paradox did, they actually took the stock server from LWIP, and they added verification functions, so the user must be logged in. So that's just some general function that uses that handles CGI calls. And you can see there is like a loop in here, and there's the extract URI parameters. And on the other end, we have the firmware. So we have the same function. Here's the loop, and here's the extract URI parameters, only with a check to see if the user is connected. So that's what they did. And what we care about is the actual authentication functions on the server on the server side. So Paradox login, as I tagged it, and now we reach our first remote code execution vulnerability. So labeled under CVE 2020-25-189. It's actually a bunch of buffer overflow vulnerabilities in the same function, the same login function. So first thing you can see in here, the str copy. Actually, what happens is that the get parameters in here are passed as a list of strings. And for each one, they take the data in the parameter and they copy it to a local a buffer with a length of 100 bytes. And that is done obviously in an unsafe manner, which leads to a buffer overflow. Now, the more interesting part, the more interesting buffer overflow is another one, which happens on the X decoding logic. So what they did in here, because they pass everything in X decoding, they actually go 2 bytes at a time and use scanf to decode the hex into 1 byte. So the thing is that the loop only stops when it's null. So it's essentially the same kind of buffer overflow. We can put as many data as we want, and they'll decode it to a limited size buffer, local buffer, which leads us to another buffer overflow. And there's another with the password also, obviously. And that's our first and major remote code execution vulnerability. The other one is actually in a pretty similar function, but it's not the same function. It's also an authentication function, but it's used when you're already authenticated and they want to kind of re-verify your authentication because it's like a high privilege function. And in here, you can see it's pretty similar, but only there is some more buffers. And that's exactly the same, like the username and password are in the linear. But besides the username and password, we also have in this function the PNL and PNP and some other possible get parameter names. I suspect it's for like an API kind of authentication maybe, or for legacy purposes. So that's great. We got 2 remote code execution vulnerabilities on the device. Now it's time to exploit them. So we need to decide what we want to do. The obvious thing in those situations would be that we want to override the LR, the return pointer. So when the function ends, it will pop back the program counter, and then we get a control over the next instruction, the instruction pointer, essentially. So we could execute our shellcode strictly. So we could execute the shellcode directly from stack. But the only problem in here is that we can't do it, because in these specific ARM chips from ST Electronics, what happens is that the memory lies in an address range which starts with a hexa 20, which in ASCII encoding means a white space. And because we're working with get parameters, we can't have white space in there. If we'll send white space, what happens is that the vulnerability won't be triggered on the server. So that's kind of a problem. And the way that I solved it, overcome it, was using a rope chain. The idea with a rope chain is to use existing parts of the firmware code. Each part is called a gadget, and we assemble them together. We jump from first gadget to the second gadget. And the nice thing is that the firmware lies in a memory area that starts with hexa 80. So we don't have a problem to jump over there. And in here, the important stuff is the loading of the stack pointer address, where our shellcode lies, into a register, and then eventually into R1, and eventually we jump using BLX, the branch instruction, the jump instruction in ARM, we jump to this address after doing some setup in here and all of that. So we start with the buffer overflow, we go to the firmware, and from the firmware we go back to the shellcode. I just wrapped it a bit so it would be nicer to use. You can see it's a Python code that handles all of the exploitation process. So except the program counter, we're also overriding all of these registers, and the exploit function would create a GET request to the alarm system, which actually puts all of the data that we need to override, and the user parameter and the password parameter as specified in here. And I wrapped everything with a function that I called safeexec that just takes code, binary code, and execute it in the memory of the device, leveraging the vulnerability and the rope gadgets. So all of the gadget addresses in the firmware are encoded, and also the code is X encoded, so it would be X decoded afterwards on the device, and it's passed as the password get parameter. So in that point, we have the vulnerability, we know how to exploit it. We're using a rope chain to safely jump back to the shellcode. And now the only thing left is to decide how we want to exploit it. So we said that the final goal is to disarm the alarm. And the easiest way, in my opinion, to do so is using an API. And for that API, we need a password. So the shellcode idea is to dump the password and send it back to the CNC, back to us as the attacker. And it could be very, very complex, because think about it. The firmware is it's a plain firmware. There's no operating systems, there's no API. And I really didn't want to mess with all of those things. So creating a reverse shell, for example, would require a lot of work. So the idea was to leverage the code that we already have in the firmware. And the way that I did it is by changing the original code flow. So originally, the user would request to log in, and then the login function would check, okay, the username and password is valid. Yes, okay. Now it would open some 401 page, and it would set it to be the page that the device should return. So the idea was that we'll change the flow. Here we have the exploit, and instead of opening and of simply opening and returning that HTML page will modify the behavior so that the HTML page actually would point to some address in memory that we know that the password is at. So every HTML page, every page that you open with the fs function fs open function actually returns a descriptor which says, okay, that's the file name, that's where the data is, that's the length of the data, ta-na-na. So we'll open some whatever page, and then we'll edit the pointer to the data and set it to, so the device would return that new modified page, which is essentially the password for memory. That's how the fsopen function, the original function from LWIP, looks like. You can see it sets all of this data in the descriptor in here, and all of what we want to do is modify this pointer. And that's the shellcode, which modifies the pointer. That's some initialization stuff, not interesting. Default HTML string in the firmware, so that's the address in the firmware. fsopen, the function in the firmware which handles the opening of a file from the VFS, which lies in that address. We just call it, like branch to it, and then changing the data pointer to our new data, which is the password. In memory, you can see that's a RAM address. And then we're continuing with the normal execution, which essentially leads to the behavior where the device returns the password, it dumps it from memory and returns it to us on the same GET request that we created to exploit the device. Now, we exploited the device, we got a password. Now, the question is, how do we disarm it? So for that, there is a bunch of projects in GitHub. I chose to use PAI, Paradox Alarm Interface, which is a really nice project. It's just like for automation purposes, for guys who want to do like home automation stuff with their alarm system. And the thing with PAI is that is the way that it works. So we exploited a port 80, like the web interface, which should be open from the public internet. But PAI works as this management software called Babyware. Babyware is Paradox management software for the alarm systems. And it's used to set up different rooms, different areas, different sensors, all of these things. But it's used locally. So port 10,000 would normally be open only on the local network, and we're on the internet. So what can we do with that? And my idea was to create another shellcode which would switch the ports. So after the first exploitation, and after we have the password, we'll exploit it again and tell it, okay, switch between port 10,000, between the service that goes on port 10,000 and the service that goes with port 80. So for that, I created this shellcode, which essentially used an update config function, which is built in the firmware, and tells it to switch the services. So now, what we get is that port 10,000, like the management port, is actually port 80, and it would be open to the public internet. And that's pretty much it. So we, just to summarize what we did up until this point, we decrypted the path with the help of our friend Nesmogos. We decoded the Intel X encoded payload. We did a man-in-the-middle attack, damped the network traffic, reverse engineered the Intel X payload. With that knowledge from the reverse engineering, we understood and decrypted the firmware from the network. Afterwards, we reverse engineered and found the vulnerability in the login handling function. we exploited this vulnerability using a rope chain that led us back to the first shellcode, which is a password dumper. It just dumped the password for us from memory and returned it on the same GET request. Then we exploited the vulnerability again, switched the ports, and now we have port 10,000 open to the public internet, and we have the device password together with the Python PAI library, and then we disarm the device. And that's pretty much it. So now it's demo time. Okay, guys, so it's demo time, and I want to do this demo really quick, so we'll have enough time for the live Q&A session. So let's start. First thing, you can see my screen with the Jupyter Notebook and all of the exploitation code in it. So we're just gonna go and execute it step by step. So you'll get a real clear view of what's going on. And if you notice, you can also see the camera view with the alarm system itself. So here we have the actual control panel, which is used to control the alarm system. And you can see we have two rooms. One is the hallway, the other one is the kitchen. Both are system off, which means the alarm is off. So I'll just go ahead and arm it. Code. Area number 1, area number 2, and we'll give it a second. Okay, and now it's armed. So if we'll go back to the Jupyter Notebook, you'll probably notice in here the exploit function and safe exec from stack, which we talked about earlier. Both are responsible to execute, to exploit the actual device. I have some utility functions in here, which are not really interesting. And target IP. So in this specific case, in this demo, I just connected the alarm directly to my laptop. But obviously in real life, we want to access it, to attack it from the public internet. And there's probably gonna be some router with some port forwarding configured on it. So we need to keep that in mind. Let's go ahead. Shellcode number 1 is the memory dumper, which we also talked about. So we can see that it was pretty quick, and we got like the HTTP response back. Those are the HTTP headers. This is the actual raw memory dump. As you can see, it's pretty raw. There's like a URL in here. There's some hex values in here. Pretty nice. And in here, if you notice, you'll see paradox, which is our password. So we'll go ahead and decode it. Paradox. This is actually the default management password for the device. So now we got a password. The other thing that we want to achieve is to switch the ports. So as we said, in real life, the ports, the management ports probably won't be accessible from the public internet. So we need to switch the management and web interface. So now it seemed to be successful. So the management port is actually opened on port 80 instead of 10,000. And the web port is on port 10,000 instead of 80. So we got pretty much everything that we wanted. We have the management password, and we can access the management port. So we'll go ahead and use Paradox Alarm Interface, which is the library that we're using to connect to the device. You can see there's some configuration that we need to do. So here is the device IP. Here is the password that we dumped using the shellcode from the device memory. And we'll go ahead and try to connect to it. You can ignore those errors. It's just a kind of an unstable device. And we got true, which means that we are now connected to the device. So we'll do a quick refresh and get the partitions. So what are those partitions? There are actually the representation of the areas that you saw. So hallway and kitchen. You can also see them on the camera view, hallway, kitchen. And what we care about is actually the key, which is the internal ID for those areas. And we really need to know it so we can disarm those partitions, those areas. So in here, we're just gonna go ahead and try to disarm the first partition, the first area, which is hallway. And you can see that we got hallway and we got system off, which means that now the alarm in the hallway is disabled, is disarmed. So we'll just proceed and we'll try to disarm the other partition. And you should look at the camera view and you'll see that kitchen switched to system off. So that's it. Everything is disarmed. And now our guys can go and breach the actual physical building, and they don't need to worry at all about the alarm system. And that's it. So thank you for watching, and I'll see you in a second in the live Q&A session. Let's see it.